very difficult to put a probability down as to how many, as to whether there's life in the universe, what the chance of life in the universe is. What you have to set against these very vast distances is the fact that our technology has advanced so rapidly that we're able to detect very faint signals right across the electromagnetic spectrum. So right from the very highest energy photons, as they're called, gamma rays, cosmic rays, all the way through to optical light, X-rays, optical light, through to radio waves at the other end of the spectrum. And that means, because that technology has advanced so much, that means we're able to pick up very faint signals. So we can see these objects very far away. It now will be possible, very soon it will be possible.
The Legate podcast is sponsored by Montrex. Montrex is a cutting-edge sportswear brand empowering athletes across the world, built to enhance performance and give you confidence to go the extra mile. They've got some of the most incredible products at montrex.com. There is a link below this video. Click the link and at checkout, enter the code LEGIT for 15% off your order. That's LEGIT, all one word. Everything from jackets, cargo pants, gym tops, t-shirts, running jackets, running pants. Everything is on their website, and they sponsor some of the most incredible athletes. Everything from UFC fighter Leon Edwards and a good friend of the podcast, boxer Jazza Dickens. So click the link below, use the code LEGIT at checkout for 15% off your order. Radio, it's a Legate podcast. We're myself, Tom Wickstead.
It's me, Andy Grant.
And this week, absolutely honoured to have Chris Collins. Thank you so much for your time, mate. I've got a written down a bit of an introduction, which I'm going to read out for people at home. So this is taken from your university sort of bio.
Oh, okay.
Right. So, yeah. So you are a professor of cosmology within the Astrophysics Research Institute, ARI, of Liverpool John Moores University. You were head of the institute between November 2016 and December 2019, also acting director between 2004 2007, and again between 2014 and 2016. Long established record in collaborative research with institutes worldwide. Research covers topics in observational cosmology, focusing on studies of the evolution of galaxies, clusters of galaxies over cosmic time, and their large-scale distribution in space. Mm-hmm. In 2009, you were the recipient of the Royal Astronomical Society Group Achievement Award as part of the 2DF Galaxy Redshift Survey Team. In itself, that's cool. UK Associate PI of the Large Synoptic Survey Telescope and lead a core team in the ARI examining optimum extraction techniques. And then some of your, I don't mean to go on here, Chris, but some of your academic appointments: Science Board Member for the Science and Technologies Facilities Council. Yeah. Mm-hmm. The ESA Observing Time Allocation Committee for the European Space Agency.
That's right.
Grant Panel, Science and Technology Facilities Council, and various chair membership for telescope allocation committees.
Yep. That's about it. Well, I'm as honoured as you are, gentlemen, to be honest. It's great to be here. And,
that's probably the cool
bit about my job, obviously, but it's also vocation, has been for many decades, since I was a wee nipper. But yes, there's astronomy really started in Liverpool in 1992 when the Astrophysics Research Institute was set up, part of Liverpool John Moores University, as you said, and we're about 100 staff now, if you include technical staff, admin staff, lecturers, researchers, PhD students. Managing that number of people is tricky in itself.
Yeah, of course.
Our research covers a wide range of astrophysics, from looking at the properties of stars, for example, the local universe, the Milky Way, properties of the Milky Way, galactic structure, properties of local galaxies, how galaxies evolve through cosmic time, right up to cosmology, studying the early universe and the universe on very large scales, which I'll probably explain to you later. So almost, the entire remit of astrophysics. We're one of the largest astrophysics institutes in the country.
Right.
We do both observations and simulations, or theory, as it's called. And one of our other sort of unique selling points is having the Liverpool telescope, which is a research-side, large research optical telescope that's situated in the Canary Islands on La Palma.
High up usually, yeah.
Yeah, and that's designed to look at transient objects. So these are essentially stars that explode or vary. They can be very energetic, but they carry out that explosion over a very short time scale. So if you can design a telescope to look at those very quickly after you've been alerted that an object has actually exploded, then you can extract a lot of physics out of these events, these very high energy events. The highest energy events are supernovae, but also we've worked on colliding black holes and
it's crazy.
Followed up.
We're 2 minutes in and I already feel incredibly stupid listening.
So the institute is very active in these areas basically. So my part of it in terms of research is actually working on the evolution of galaxies, the change in the structure of the universe over cosmic time.
Well, one of the we all probably when you were younger have a teacher that sort of stands out to us when we were in school, college, whatever. When I did physics A level for a short period of time, there was a guy called Mr. Anderson who incredible teacher, and one of the first ever sort of, obviously physics in A level tends to not really be too much about space, but one of the things that always blew my mind, and I've written it down here just because space you just cannot comprehend. It bends your mind.
I get a headache when you think that much of.
So for example, and I've written it down, and again I had to go on Google just to get the facts right because my memory's a little bit hazy. So the Milky Way, obviously our galaxy, is the diameter, how big it is across, is 105,000 light years across. There's according to space.com, there's around about 100 billion stars within our galaxy, similar amount of planets. The nearest galaxy to us, Earth, is the Andromeda Galaxy, which is 2.5 million light years away. And then astronomers say there are maybe like 100 billion to 200 billion galaxies in the universe.
That's about right. Those statistics are quite good. So remember, a light year is in this context is a measure of the distance an object is, as you say. So it's the distance light travels in 1 year. So just to give you the context of that, just to take other examples, it takes light about 8 minutes to reach us from the sun. So this bright light we're seeing at the moment.
28
if anyone's watching, that's why I'm
29
sweating.
degrees, yeah. That's caused by radiation hitting the Earth, obviously, but it was emitted by the sun 8 minutes before. If we go to the...
So how long then is 1 light year?
So the distance... Well, one light year is basically the distance light travels in one year.
Okay.
And light travels at a speed of about 300,000 kilometres per second. So you can do the maths. But if you go to the outer planets, for example, it takes about an hour for light to travel from them to us. That they don't emit light, they reflect it from the sun. But when through a telescope we see pictures of Jupiter and Saturn, it's about that time period. If you go to the nearest star, then you jump from a few hours light travel time to a distance equivalent to about 4 light years, 4.2 light years is the distance of the light travel time to the nearest star, called Proxima Centauri.
My head's already fell off here. This is...
So you're only 4.2 light years away, and that's still the closest star. Now that star's actually on the Australian flag. The Australian flag has a series of stars, and it has essentially the Union Jack in one corner. One of those stars is Proxima Centauri.
Why is that?
I don't know. It's just the way they designed it. I'm not sure why. It's part of there's a constellation called the Southern. Well, it's a series of stars called the Southern Cross, which you can. It's located towards the centre of the Milky Way. Can't see it from Great Britain, but from the Southern Hemisphere, you can see it quite easily. So that's depicted as well. But we're only 4.2 We're only 4.2 years. You see, at the nearest star. And as Tom said, if you want to go to the nearest galaxy, you go from 4.2 years to million years, 2 million years.
And again...
so it's a massive difference. And in terms of the subject I study, that's just on the doorstep still. The Andromeda Galaxy, our nearest big galaxy, is on the doorstep still, as far as cosmology is concerned. It's a study of everything larger than that, further away.
It's so difficult to just wrap your head around even that, isn't it?
It is. I mean, I have trouble with it and grappling with it for 40 years. The distances are so huge.
Well, that's for me, even just 1 light year. So how far light can travel in a year? That's one.
Yeah, one unit.
1 unit, yeah. I mean, that's a long distance.
So 300,000 kilometres per second.
For a year.
I don't know how many seconds are in a year.
Yeah, 3 times 10 to the 7. That I do know, so you can multiply it out.
Jesus Christ.
Like, that's a fucking long way.
Enormous. It's not worth calculating it because it won't mean anything when you do. It's just so far.
So the thing is people always say, don't they, like, is there... Again, I know this isn't your speciality, Chris, but, like, people always say, like... You know, is there extraterrestrial life? Is there cell life? Blah blah blah. So if there is a civilization similar to us that can emit signals like radio signals, things like that, then the nearest galaxy to us is 2.5 million light years away. So it would take that signal 2.5 million years to reach us.
That's correct. Yeah, it would.
Before we even hear anything from them.
Yeah, I think that's right. It's very difficult to put a probability down as to how many, as to whether there's life in the universe, what the chance of life in the universe is. What you have to set against these very vast distances is the fact that our technology has advanced so rapidly that we're able to detect very faint signals right across the electromagnetic spectrum. So right from the very highest energy photons, as they're called, gamma rays, cosmic rays, all the way through to optical light, X-rays, optical light, through to radio waves at the other end of the spectrum. And that means, because that technology has advanced so much, that means we're able to pick up very faint signals. So we can see these objects very far away. It now will be possible, very soon it will be possible. We found there are Earth-like planets around other stars. Okay, so obviously the Earth is a certain size, and we orbit our sun, and there's obviously life on Earth. We don't know there's life anywhere else. But if you just start asking the question, well, are there planets like our own going around other stars? And the answer we now know is definitely yes. The question is, what's their atmospheric composition? And that's really what the current observations, and certainly the next generation of instruments and telescope observatories, are going to address. There's various planned.
Is it right that they call it the Goldilocks effect? Because it's just right.
Yes, it is.
That's me trying to be clever. That's the
not too the porridge, not too hot, not too cold. That's quite right. Yeah,
I was told that when I went to. I actually got to go to NASA, which was quite cool. Yeah,
well,
got to go
hand over to you then.
Mission. I had to try and get that in, try and one up you there. But no, he basically said, we got to go mission control, and he was explaining that. You know, for there to be life on Earth, it's got to be just right, not too hot, not too cold.
Yeah,
to call it the Goldilocks.
That's exactly right. But we seem to be in what's called the habitable zone. So, we think there's no life on Venus, basically. It's further into the sun. It's too hot. We think there's no life at the moment on Mars. There's obviously missions to Mars to try and see for water, which may be frozen under the surface. And it may be that water contains microbes, possibly contains life. But we know there's no intelligent life there. It hasn't had a chance to develop. And that's right. So we're, as it were, just right, just like the Goldilocks story.
It'd be incredibly naive, I think, to think that there's not, when you talk about all those other galaxies, and incredibly naive to think we are the only ones in this whole solar system.
Yeah, I think that's right, and that's the trouble, that even though you might say, well, if you work out the probability of life on a particular planet, or you need a very, you need a habitable zone around a particular star, because the star can't be too hot, can't be too cold itself, has to have certain properties. Opposing that is the fact that there's billions and billions of stars, so you may just have individual stars dotted around that do exactly have a planet at the right distance in their habitable zone, in this habitable zone. But it's a very fertile area of research that's currently growing. But as you said, Tom, it's not my area of expertise.
Yeah.
But it's a very interesting part.
It's incredibly interesting.
Astrophysics.
I know. Wasn't it Voyager that sent that like a gold disc?
Yeah, it was
with human sounds, songs.
Yeah, amazing.
And a gold plaque on how to actually read the record. And
it's quite demoralising, though, that I didn't realise the fact that, though, if there was anything from the nearest galaxy, we're going to be waiting 2.5 million years to get that message.
Yeah, well, even longer with Voyager, because it's just it's not going as quick as light. The limiting factor here to all of this is light, isn't it? If something could go quicker than light,
that's where time travel comes in, though, isn't it? Then, am I right?
There is a thing called time dilation. It's part of what Einstein was the first to realise about time dilation and what he called special relativity. So yes, you can't travel faster than light. That if you try and approach the speed of light, if you get in a capsule and try and approach the speed of light, you need more and more energy to do so. So for a piece of material, for you or I or whatever, a piece of matter to approach the speed of light, you need an infinite, or to reach the speed of light, you actually need an infinite amount of energy to do so. So you can't.
I'm sorry, I don't understand how. I mean, you can't.
So So what happens is that the mass increases basically as you approach the speed of light. The mass increases. This is due to it's part of what's called time dilation. So what happens is, if you start travelling towards a star, let's explain it this way, or maybe just perplex you this way. But
probably, yeah. I apologise, by the way.
No, it's a good question. If you take a twin, two twins, a pair of twins, and you put one in, so exactly the same age, born at the same time, and you put one in a spaceship, and you send them off into space, let's say they travel high speed out for 5 years as you measure it back here on Earth, and they come back after 5 years. So on Earth they've spent 10 years away. When that twin gets out of the spaceship, you would expect them to still be the same age, but in fact they won't be. The twin, if you approach the speed of light, if you travel fast enough, not faster than light, you can still travel slower than light, but if you approach the speed of light and they come back, they'll be younger. It sounds crazy, but they will actually not have aged at the same rate, and the reason is because the passage of time is relative to what's called your inertial frame, or basically how fast you're travelling. So what this means is that if they was, I mean, you can try and design it a little bit more carefully and think of the two twins exchanging, messages, television messages, as they travel away and back. And if you look at that process carefully enough, what you see is when the spaceship turns around and travels back, they start seeing a very rapid increase in the arrival of photons from Earth, because they're travelling towards all these photons. It's a bit like a Doppler shift of a car, when a police car siren travels past you. There's quite a few in Liverpool, right? When they're travelling towards you, it's higher pitch, but when they travel away from you, it's lower pitch. Well, that higher pitch of sound simply means that the sound is arriving quicker. It's the same with light. as the spaceship travels back towards Earth, it picks up more and more photons, and it sees a much quicker passage of time on Earth through a monitor screen that you view if they were exchanging signals. So anyway, if you do that calculation correctly, you can come up with a formula that relates the passage of time on the spaceship compared to the passage of time on Earth, which is just determined by the speed of the spaceship relative to Earth. Yeah. So,
that is insane about it. I think again, it's something about space where your mind just can't, because it's.
I feel so stupid right now.
It's not it's not normal, isn't it? Do you know what I mean?
It's not normal. It's not, and it's you have to. I mean, I got first interested in astronomy. I mean, you were talking about a motivational teacher, and I think for all young people, all children, and so on, it's so good to have. Yeah, there are some really inspirational teachers around, I have to say. I know some of them in the area at Merseyside. But when I was little, we had a really good teacher who would just simply encourage us to ask questions. He wasn't an astronomer particularly. And that just got me thinking about space and so on. And I remember the other big person who inspired me was my father, my dad. And I remember I couldn't have been more than about 7, 9, something like that, of a Saturday morning, sitting on the side of his bed. My mum had probably gone down to make the breakfast, and he used to tell me about the Earth being on the spiral arm of a galaxy, like a big Catherine wheel called the Milky Way, and it was turning round. And I just become absorbed by that, and started sort of just reading a few astronomical books. Patrick Moore was the all in at the time, and The Sky at Night I think was still going. And then of course when I was 9 were the moon landings, so I was of that generation, and I was captivated by that at an early age. But
must have been amazing to see that as it was going on.
It was, yeah. I mean, I remember the quality of the TV wasn't very good at the time. There's big horizontal, grey lines on the TV. But I remember staying up and seeing the famous words that Neil Armstrong spoke. As he stood on the moon. And then I just decided to do. I mean, I was better at the sciences than I was at arts and languages and so on at school, and so I did physics O levels then and A levels, and then went to university to study physics. I went to Imperial College in London, graduated there, did a PhD there in the astrophysics group. And when I was at Imperial, I got involved in all sorts of things. It was actually I was lucky to get back into astronomy. I wasn't intending to do that when I was an undergraduate there, because I was just absorbed in a huge amount of interesting types of physics. But I just wanted to pursue it because it was a challenge, and I thought, can I really do this? This is interesting. And I was always try and say to young people, if I'm in schools or just talking to undergraduates or potential undergraduates, do what you're interested in. Do it because you're interested in it. That's the main criteria. If you want to study a subject like astrophysics, it's infinitely fascinating. And then from Imperial, I went to Edinburgh. I was 6 years in Edinburgh as a research fellow, both at the Royal Observatory, Edinburgh, and the physics department there. So one job followed another there. And then in '94 I moved to Liverpool John Moores.
Been here ever since?
I've been here ever since, yeah. 27 years it is now.
I guess in your field, I mean, you'd never become... I mean, I suppose you could argue that for most fields, but especially yours, you are constantly learning new things, I'm imagining.
I think that's right. I mean, a good example of that is I taught cosmology, relativity and cosmology for a number of years, but the subjects changed during that period significantly. So at the time I first started teaching it, we had no matter, this matter around us. We had what's called dark matter. Dark matter has been known about since the 1930s. So dark matter is a form of matter that seems to dominate the universe, but it doesn't shine. We know it's there because gravitationally it acts just like ordinary matter, the sort of stuff you and I are made of, and everyone else, everything's made of that we see. But it doesn't shine, but it's there, and it dominates the ordinary, what we call ordinary matter. So we've known about that since the 1930s. What we didn't know about, there was results that came about from studying distant galaxies and stars that explode in those distant galaxies, was that there seems to be a force that's actually causing the universe not just to expand, we've been known as it's been expanding for, again, decades, many decades, but that expansion is accelerating. It's actually getting quicker as time goes on. And that's due, we think, to something called dark energy. So that the natural interpretation is effectively what's happening is the vacuum of space itself is pushing galaxies apart at an ever-increasing rate. And we think, given the measurements that we currently have, that acceleration will just continue into the future. Forever, yeah.
Right.
Yeah. Now, there's different interpretations of what this dark energy could be. It could relate to some theories of particle physics, and be something related to what's called a scalar field, and we'll go into that. But it could be something that we're on the verge of understanding, or it could be something that's completely new and we've not really yet got to the bottom of the physics. There's more physics to be understood at a very fundamental level. So it's an exciting time to be in the subject, because even as I say, even me talking to undergraduates during the lifetime of the course, I had to change what I was telling them as these discoveries were being made. And that's a great thing about lecturing, if you're a researcher, because not only do you get to do the research and motivate PhD students and other younger researchers. You motivate the undergraduates, because you can go into an undergraduate lecture and tell them about the work that you've been doing. And my colleagues and I try and do that as much as we can, both to undergraduate students and distance learning students. We have students from all over the world who take courses online. And again, they're interested in not just in the basic astrophysics, but in the results that are coming through.
On that, what has been, since you got into this, what has been the most startling or interesting discovery that's changed in your lifetime, where you thought, wow, this is incredible?
I think there are three things. I think that dark energy wasn't so much a single discovery. There were experiments that showed that there was a natural interpretation in terms of a dark energy. So that would certainly be one that I've described. Two others. One most recently would be the discovery of gravitational waves. So for decades, physicists have been trying to detect a special, unique type of radiation. We think of radiation as being electromagnetic radiation, as I mentioned before, so X-rays, optical lights from the sun, radio waves, and so on. But there's another type of radiation which is linked to gravity. So if you if you imagine just getting a big, massive object and just sort of shaking it, or taking like a big, massive dumbbell and twirling it round, or a big, massive star exploding, it sends out gravity waves. But these are very, very tiny signals. If you the gravity detectors are built around big interferometers, so they're big like an L-shaped, two arms in an L, and those
similar to what I've got up here on the computer.
That's Lisa there, the second one along.
Second one, yeah.
Yeah, which is a design for gravitational waves in space. The two big operational gravitational waves, gravitational observatories for which gravitational radiation has been detected. The two instruments involved were Virgo and LIGO, the two big gravitational operations. But you're talking about measuring essentially the interference pattern of an interferometer over the two arms separated by a couple of kilometers or something, and the oscillations that are induced by the gravitational wave coming from the other side of the cosmos and passing through the Earth and affecting the gravitational detector are less than the size of an atom, of one atom. That's how much it's vibrating. You can detect it because the length of the arm of the detector is so long. So you've got a long. You're essentially amplifying the signal. But these are very small signals, and it's taken a lot of physicists over many years. Some colleagues I know have worked on it their whole lives, trying to design a sensitive enough experiments to measure gravitational waves. And the discovery of those was a few years ago. It was 2017, I think it was.
Right.
And that was a big breakthrough, because we then knew that as a community we understood gravity at a far deeper level than we previously had.
Right.
And there's going to be many more gravitational wave experiments and much more insight gained into, for example, black holes. The signal comes essentially from the coalescence of massive stars. So many stars are in binaries. You could think of them moving around each other, a bit like a dumbbell, the analogy again. But as time goes on, the energy is radiated, so they actually start moving together, and eventually they collide. And if they're massive enough, that collision causes so much energy, gravitational energy, to be released. You detect the gravitational wave, but what you're left with is a black hole. And in some cases, what we think's been discovered is that there's no big explosion at all. It's just a detection of gravitational radiation with no optical counterpart radiation.
Is that because they've added the old thing is that black holes don't give out any light?
Exactly.
Because they've got such a strong gravity pull that they pull the light in, so you can't see them.
That's right. So if you take two isolated gravitation black holes and you just bring them together without any radiation or matter around them, what will happen is they will just form a bigger black hole. You won't be able to detect it with conventional detectors of the detecting light and electromagnetic radiation at all, because it doesn't emit any. What it emits is gravitational radiation, and that's now been picked up.
So that's a way that we can then see black holes in a sea, for want of a better phrase, black holes, yeah.
That's right, and the detections are modelled in computers, and you compare the computer model to the observations, and you can deduce things like the relative masses of the black hole merger and so on. So over time, you build up a portfolio of these events, and that gives you that tells you a lot about the late time life cycle of very massive stars, which in turn feeds into our knowledge of stellar evolution and stellar astrophysics.
Goodness me. And it says here space-time. So what is space-time then? Sounds so cool, space-time.
So it's literally, so if you think about, I think the simplest way of saying it is, if you go back to what I said earlier about special relativity, remember we had this link between space and time, in that you can, depending on how, depending on the relative speeds of objects, you've got changes in
time.
Passage of time. Well, if you include gravity in that equation, if you say, okay, we live in we're applying in the case of special relativity that to what we call inertial frames. So those frames simply exist in a space. That's the assumption, and that's a good enough assumption. But if you think about here on Earth, for example, it's not free space. We have a gravitational field pulling us to the centre of the Earth. That's why we're able to sit down, not float around. But the interesting thing there is what the gravity is effectively doing. It's essentially warping the space. That's what gravity does. That's what mass does. It warps the local space. And so it actually causes a similar type of time dilation as I mentioned before in special relativity. Things actually travel slightly slower. Time passes slower for something close to a big gravitational field than it does for things further out. And in fact, your GPS that tells you your location actually has in it a correction for a general relativistic effect. Yeah. So it's not a big effect. It's not a big effect. It's a tiny fraction of a second over a long time. But nonetheless, it is there, and it is measurable. It's very measurable.
The way in its sense that time can slow down is just you just can't. There's so many times you just can't.
You know what this conversation reminds me of a little bit? The film Interstellar. You seen that one?
Not seen it.
With Bradley. Is it Bradley Cooper? Is it?
Possibly. I don't.
Not Bradley Cooper. Matthew McConaughey.
I've never seen it.
That was a film that I had to watch a couple of times because it just hurt. It was all about different speeds and stuff and time travel. And
so, Chris, in a black hole, then does time go slower then?
Yes, that's right. So if you've got a black hole out there out in space, and you wouldn't notice anything if you're away from the black hole, but as you if someone travelled towards it, for example, they would enter the black hole and disappear, as far as they were concerned, very quickly, undergoing what's been called spaghettification. So that actually their head would have a different gravitational pull from the black hole to their feet. So they'll be stretched. Very very careful, quick way of toning up your muscles and looking shapely. But so they will fall into the black hole. But as far as you perceiving them are concerned, you will actually just see them falling in at slower and slower and slower rate. So if they were waving, they would be waving slower and slower and eventually just stop. What's going on?
God!
Will actually finally disappear. So it's not a fate that you really want to.
And
Stephen Hawking did a lot of work in this, of course, in this area. A very famous physicist, of course, and his own personal story alongside that. But
you say just disappear. I think I just imagine the comments are going to be Andy asks such stupid questions. When you say disappear, what do you mean disappear?
Well, you
just vanish into.
Well, a black hole has the property that nothing can escape from it except including light itself. That's why it's black. So you can't exchange information with someone who's fallen into a black hole. That's what I mean by disappear. It really is like falling down a hole, the biggest hole you've ever fallen down. You can't just climb back out. There's no ladder to get back out.
So once a black hole's consumed something, you ain't getting it back.
No.
But where's it all going?
Well, it's gone through something called the event horizon. There is a theory, an idea that what happens eventually is that the black hole eventually radiates the material away, and the idea is that the black hole will eventually explode, and all that material that it's sucked up will be catastrophically thrown across the local universe. There's believed to be a black hole, large black holes, at the centre of most galaxies, including our own. There's evidence that there's several million solar mass, so a million suns basically packed into a very small area. And there's dynamical studies that have done showing the passage of stars in the vicinity that have concluded there must be a very concentrated massive object of a million solar masses at the centre of our galaxy, which is equivalent to the properties of a black hole. So black holes are ubiquitous. It wasn't direct evidence, circumstantial evidence really, until we actually discovered gravitational waves, because they can only come from something of that.
And have we got what's the closest black hole we've got in our? Have we got one in our Milky Way? One that's
it's about 8 kiloparsecs away. So you're all right. 8,000 parsecs. So that's about that's a few thousand light years.
And there's no chance of us getting pulled towards that or anything anytime soon, or
not anytime soon.
Making sure.
You'd be okay,
going on holiday next week.
But if we were heading towards a black hole, we wouldn't really know about it, would we?
Well, you would, yeah. When the gravity would get stronger and stronger and stronger, so it would be it would be like the worst fairground ride that you could imagine, right? So you would actually be physically pulled apart. So in the later stages, not as you were heading.
But if we're slowly heading towards it, it's not suddenly like everyone wakes up. God, I feel a bit heavy today.
No, that's right. As long as you're not too close, it will be okay. But if you get too close, then the gravity will take over. The closer you get, the worse it gets.
I read something, Chris, that there's the reverse of a black hole, which is a white hole. Which is a black hole in reverse.
Starting to understand the black ones, yeah.
Yeah. So I think that we don't yet understand. Going back, retreating a little bit here, but we don't yet. No, it's okay. We don't yet. The point about a black hole is that it works at a very small level. In other words, what you're doing is you're essentially crushing space as far as you can to the point at which it's no longer contiguous. It's no longer extended. And we don't yet have a good understanding of the physics at that level. So, as a result of that, one idea is that you have black holes and white holes. That means that this material that I mentioned that must eventually come out of a black hole doesn't come out in the same black hole. It's not the same black hole that explodes as material that went into it. It's something else that explodes. And one idea is that that's a white hole. That's what it's been called.
That is incredible.
That sounds a bit like that's kind of maybe my immature kind of hat on, thinking you go into this one black hole and you pop out somewhere else in this white hole or something.
Exactly. Yeah, that kind of space travel is what's speculated. There's no evidence for it, okay, and it's just that the laws of physics don't preclude it. I think that's as much as you can say.
I think what's so difficult when you're talking about things like this is it's so hard. The numbers you're talking about and the distances and the speeds.
Yeah,
it's so hard, isn't it, to even grasp?
It is. Yeah, it is.
Because when you're saying before, you get a kind of headache. I genuinely, when you think, I don't know, when you're trying to measure something, and you go, yeah, but what's after that? And then, but then what's that linked to? What's that? And it's just this endless of, but where does it stop? Like, where does it stop? It's crazy.
It's as if you just kind of have to accept. You're fighting this thing about but why does time? So if you just you just got to accept. You got
to get. I mean, what we try and teach, in a lot of the popular astronomy books, the good ones, it teaches it quite well. It's this idea of a lot of people have, and it's a common misconception, that you can travel to the edge of the universe. You see, so they think of the universe as basically spherical, a sphere that we're inside because we look out into the universe, and that's fine. But then the obvious question is, well, what's outside the universe? Or equivalently, what's the universe expanding into? There are all these galaxies in the universe flying apart. What are they expanding into? And the answer to that is in some ways very elegant, and in other ways I think people see it as a bit of a cop-out. And the answer is that the question doesn't quite make sense. And if I explain why, imagine having a balloon, for example, and you put stick little coins on the balloon. You blow it up a little bit and then stick little coins on it, and all the little coins are galaxies. And then you blow the balloon up again. Well, if you then ask, if I walk along the surface of the balloon, can I get to the edge of the universe, assuming that the surface of the balloon is equivalent to three-dimensional universe? And the answer, of course, is no. You just keep going round. You come back to where you were. And it's a bit the same in the universe. If you carry on travelling in a certain direction, no matter where you go to, like travelling on the surface of a balloon, you see the same picture. No matter where you are on the balloon, you just see galaxies, just your buttons, and if it's a real balloon. Blow the balloon up and the buttons get further apart, but they roughly, it still looks the same on the surface, no matter where you are on the surface, and it's the same in the universe. So if you travel to a distant galaxy, even though you might think that that's on the edge of your visible universe, just like if you looked on a balloon and you looked at the surface that was towards the edge of the balloon, it might look like you're looking at the edge of the balloon, but when you walk to that, you're still on the surface. So you're still in the universe. So the universe looks the same for all observers in the universe, no matter where you are. And that is
that's a good way to show you.
Quite revealing.
Almost having, like, if you just kept on blowing this balloon up, if you like, it's just the biggest balloon ever. So you constantly never really.
That's right.
Getting to the end.
You
of
never
it,
get to
almost.
the end. Yeah.
That's right. Yeah, that's right.
See that? Yeah, I can understand that. It's explained
it's
to
a
me.
very good way of putting it.
Yeah, it is a reasonable way of putting it. I think so. But you mustn't get the idea that the galaxies and the planets and us are being stretched in any way by the expansion. That's not what's happening. These are very large-scale effects of the expansion. And galaxies, on the scale of galaxies, you can just think of them as just moving apart. Right? So it's because if you draw galaxies on the surface of a balloon, draw spots or something, the spots themselves will get bigger as the balloon expands. Yeah. So it's not like that. But it's a good analogy, yes, in terms of showing what happens with a uniform expansion and what happens in terms of walking around and trying to understand why we can't look at the why we can't walk to the edge of the universe.
Edge of the universe, yeah.
It doesn't really exist.
Because another big one is people always say, I've heard the question of Big Bang happened 13 billion years ago, created the I'm getting this wrong, created the universe, but what was here before the Big Bang? Like what was in this space? And then everyone talks like this in all of everything that we see around us, all the billions of galaxies, all came from something as small as an atom that just exploded.
Yes.
And then it's created all this.
Yes. We don't have an agreed theory for what happened before the Big Bang.
It was God, wasn't it? Didn't God just click his fingers?
There are scientific equivalents to that, but they're not. The problem is when you get to that level of speculation is really to have a scientific theory that is a good one. It has to make predictions. Any scientific theory has to make predictions. If it doesn't, then it's not a good theory. I mean, at a fundamental level, I don't just mean that it's wrong. It's not really a scientific theory.
Well, as in you've got to kind of know what you're talking about to kind of be able to say this is what's going to happen in the future because I understand it, and this is what's going to happen in the future.
Yeah, it's got to be able to predict something that you can go and observe and verify. If it doesn't do that, well, what's the point of your theory? Anyone can have an idea. I mean, this is what separates science from other forms of investigation. There's nothing wrong with other forms of investigation. There's nothing wrong with a faith-based view of the universe at all. It's simply that you've got to play the rules of the game, and a good scientific theory will predict something. Bertrand Russell, famous philosopher, talked about a lecture he gave when he was trying to explain the solar system and so on and the planets, and some woman got up at the back and said, "You're absolutely wrong, Mr. Russell." They said, "You may be very clever, but you're wrong." She said, "It's turtles." He said, the Earth is held up by a stack of turtles underneath the Earth, holding it up," and she walked out. Well, that's actually a good theory. It's not because you can go and check it. You can go see, well, is it? Maybe it is. Let's go and have a look. And of course, it's not surprising that when you go and look, you don't find any turtles, and so you can discount that theory. But it's not a bad theory. I mean, we have a theory of electrons, and Stephen Hawking said in his book, The Brief History of Time, we haven't seen an electron either. We haven't seen turtles, we haven't seen an electron. But the point about a theory of electrons, it makes predictions that we can then go and follow up, and lo and behold, the experiment suggests that yes, there is something in the idea of electrons. So you've got to be careful, I think, in these, when people... your science is actually quite a rigid set of rules that you have to abide by to play the game.
How have you found out in your career when it comes to religion? I mean, if you are, I don't know if you're religious yourself, or you've come across maybe students who are, or people, or does just the very nature of what you're studying take away that kind of religious aspect of someone's life?
Well, I think they're not. I think they're very compatible. Is the way I would say it. I think a view of your existence. Einstein, for example, I take his view. He said that you needed both. He said that religion without science was lame, and science without religion was blind. And I think there's a lot in that. I think they're two sides of the same coin. We find ourselves living on Earth. It's a bewildering place. There's nothing that we've found that excludes the existence of God. I mean, this is my opinion. My colleagues take a different opinion, no doubt. But for my way of thinking, there's nothing that precludes a genuine faith that is sincere and is part of how we try and understand space, a place in the universe,
and our existence.
Exactly.
I mean, the amount of times I've been on a summer's. I mean, today's a good example. Being on a summer's evening, it started to get dark, maybe 9, half 9. Sat round a chimney and you look up and you think, like, what are we doing here? Yeah. Like, how is all this happening? Yeah. And that famous thing is, we're just a group of monkeys clinging to a rock flying through space. Like, don't worry about anything. And you just look up and you think, you see all these stars, you see shooting stars, and then you look back at Earth and you think, this is just insane. Even just the thought, we're in this studio here having a podcast with 2 cameras, with you, Andy, myself. Yeah. That in itself is, it's in a galaxy that we don't really know too much about, and there's hundreds of billions of galaxies. And we make phone calls. We have a podcast? Like, what is all this? Yeah,
and it's precisely that wonder that drove scientific inquiry. We have analytical minds. We have imaginative minds. If you like, God has given us those to examine and observe the universe and try and make sense of it. I think that's it's a natural part of being human to do that, and to not rule out things that parts of existence and parts of our what makes us human, not to rule those out. Because at the end of the day, we there's still enormous amounts we don't know.
And then also, like, I was thinking, imagine if we are, I know we're coming back to, like, if we're the only thing in the universe, like, are we the only, coming back to that, excuse me, imagine if we actually are the only thing in the universe.
The only life.
How incredibly special that is. Yeah, it is. That we've come from, like, primordial, like, underground sort of volcano that created some sort of cells, and then we came into sort of more developed cells with photosynthesis and all this crazy stuff, and then how we've created this incredible world where we can get on a plane, like, it's just incredibly special.
And then how incredibly depressing is it when Donald Trump's then in charge of it all?
Well,
no, I know what you mean. No, it is. Yeah, it's.
Yeah. If we are hundreds of billions of all this, the incredible probabilities, for us to be here, and we're the only thing in the universe.
Absolutely.
how that needs to be protected.
And for us, I mean, whether it's biological or not, it doesn't really matter. The argument, it's still the fact that we have the capacity to comprehend the universe in a really extraordinary way. And that's, for me, throughout my career, that's been a privilege. That's been an absolute privilege to do that. Because it's not something I've never taken it lightly. You're using, university departments use at the end of the day public resources in order to investigate, do research, carry out research. I've been to observatories all over the world, but you do it because it's there and it's actually interesting, and it makes us more. It brings us a greater benefit, both physical and also I think mentally as well, just in terms of our increasing our capacity as humans.
And it's kind of like a form of like adventure, really, isn't it? Because there's something out there that you don't know about, and you want to find out what's out there.
That's right. Yeah, it is. It's a quest, isn't it?
It's a quest, yeah,
exactly
100%.
Like physical quests of climbing Everest and going to the North South Pole and that kind of thing that we did. Yeah, it is. It's a fundamental part of
on that note, then, and
inquiry.
I think you've nailed the religion aspect brilliant on it. On that same level of explaining things throughout your career, how then frustrating is it, or is it do you have the same view on it like you did with religion, when people come at you with flat Earth theories of things that you've studied your whole life in, and it's clearly Because I did have to ask, because there's people who, there's a trend now, isn't there? So
I think what you have to say is it comes back down to a more general point, which is what kind of answer are you looking for? There's no doubt that other people have different views about different things, but if you want to be scientific about something, if you want to play the game, you've got to have evidence. It's like the turtles again. And the trouble with things like the flat Earth theory, or that there was no Big Bang, or things like that, is that the evidence is stacked against those ideas. That's the problem. So extraordinarily in the case of flat Earth, for example, because we fly planes with computer code that actually has embedded in it a spherical Earth, right? That's otherwise it wouldn't fly properly. And then they say, well, it's conspiracy, blah blah blah. And you think, well, who are you kidding? Right? Who's involved in this conspiracy, and what's the evidence? And the trouble is, if you come, if you just act like a sort of gadfly and you say, well, I'm going to pick here and pick there and pick, you just move around. So you can try and you could close a part of that debate down, I think. But then, if people wanted to just be bloody minded about it, they just go off and pick something else to say, well, that's uncertain. It's like the landings on the moon, for example. There's people who said it didn't really happen.
Why do you think that, though, in particular, has got such big?
I think because it was, well, for several reasons. I think it's just it has a mystical element, the whole thing, the idea of leaving the Earth and going to another body and landing on it and coming back. I mean, just think, the astronauts who did it were mostly high altitude test pilots, so they knew what they were doing technically. But they just imagine the psychological impact that must have had on the astronauts, or the first three, let's say. Armstrong, Aldrin, and Collins, my namesake, although no relation. It's amazing, and so they, I think, I think Armstrong, I'm not an expert, I think Armstrong really became a recluse, and the others, I know, were hounded by people saying, you didn't really go, did you? And I've seen footage of...
Yeah, there is a few, I've seen footage as well.
Really, yeah?
Yeah.
You're hounded a bit with it, were they?
They're trolled, I guess.
I think,
didn't really go.
Didn't Armstrong, there was a video where he punched someone or something? Like,
I think there is.
Someone came up and said, you didn't really go, and obviously he lost it.
Imagine being like, you're the one who's been out of this, all these crazy numbers we spoke about, you actually do it,
But you know, what else would you do? I mean, where would your ambition be when you came back? You'd have to completely reset everything, wouldn't you, in your own mind? Because if you've gone to the moon and come back, it's like, well,
you've completed life, I guess.
What else is there to achieve? So I think there's that side of it, and I think that does attract kind of speculation about what might have happened. But I mean, the moon, the Apollo moon landings involved thousands and thousands of people. If there was a conspiracy, you would think some of them would want to make money and get famous and actually come up with some evidence.
I think it's like, because with the conspiracy stuff with the flat Earth and the moon landings, it's because I can kind of understand a little bit where it comes from, in the sense that it's so hard to understand the reality and the truth.
I think that's true. Yeah, I do think that's
maybe a lot easier, a bit easier to think, well...
It gives... people can take control a little bit if they say, well, actually, there's this alternative explanation. But the trouble is with those alternative explanations is they're just not as good. It's like a court of law. You may come up with... I don't know, it was Miss Scarlet in the study or something with the knife, if you remember in the old Cluedo games or something, but that's not what the evidence says. The evidence is elsewhere. And, in terms of conspiracies, I know throughout astronomy and the physical sciences, there's enough young researchers without permanent positions that if there was a conspiracy going on and there was really alternative explanations, they would be onto it because they want to get notoriety and get permanent positions, because there aren't many permanent jobs around. So there's no
the thing with conspiracy theorists, and it's like some of them, there's that many people,
surely someone would say something.
Too many people that are involved.
I think that's right. That's certainly true with Apollo. I don't really see how I don't really see how it could hold together. People would just they just tell. There's no doubt about it.
One of the I've just googled it now because I just had to. Is like, was it Collins who was classed as the loneliest person in the in the solar system, because he stayed in the capsule. They landed on the moon, and he went round the moon on his own, didn't he?
He did, yeah. He circled the moon in the capsule.
What? Hang on. He's on one lap on his own.
Yeah, and he was the loneliest person in the solar system because he was on his own.
Yeah.
You know what I think though, and it probably just fuels some of the conspiracy stuff. You know the way you hear stuff now with technology.
Yeah.
And you've got more power in your phone than what they had to going up there.
Yeah.
I mean, that just blows my mind.
True. Yeah, that's true. I mean, you talked earlier, Tom, about the Pioneer Voyager mission. Voyager missions. I mean, the technology there. Never mind a phone, but a small handheld calculator has far more processing power than
Voyager.
How did they do it then?
And they had to reprogram it because cosmic rays used to hit the memory locations, the memory chips on board, and so they had to keep reprogramming it to take that into account. So it's very simple technology, but the programming and the...
Have you seen this, Andy? This is that is the gold disc, isn't it? That they put on there.
Yeah, that's it. That's in Voyager. Yeah,
that's in Voyager, and they included a record, didn't they? I know we talked about this before, but they included a record.
They did.
So like that's the icon to whoever finds this. I mean, it's quite. I don't know if Anyway.
Yeah. Didn't they include? Sounds of nature, like a whale.
Yeah, a whale. Yeah. The United Nations General gave some speech on it as well, saying we're here for friendliness and we're.
Yeah, that's right.
Are they hoping that's going to crash land on another planet?
And someone's going to find it. Yeah.
It's going towards a stellar system. I'm not sure quite when it gets there, but it won't be. It won't be.
So that like thing there, that's basically to show where Earth is in the solar system, isn't it? And then
that's right. From called pulsars. That's right. Yeah.
And are they hydrogen atoms?
Yeah, I think that's right. Yeah.
So there is. Yeah.
What is the kind of goal? And is it just to kind of? Because obviously we're not sending people to the moon anymore, are we? Is it more like in your field now, just searching for?
Yeah, we're not doing that. That's right. I think when the first moon landings went there, it was just exploration, really. But I don't think for a long time since then, there's not really been any scientific reason for going back. We're actually monitoring the distance between the Earth and the Moon. There's crystals on the Moon that the astronauts put there, and we still measure that. We still measure that distance. So that's something that's going on, which tells us about, gives us information about theories of gravity and so on still. But that stopped. So I think the next phase of space exploration is to do with mining, really. It's to do with the fact that there's an abundance of heavy metals in space, and rocks and asteroids and planets and so on in general, the outer planets, and they're worth a lot of money to us. So
like diamonds, those sort of things, gold, or
all the heavy metals, for example, that go into building batteries, and battery technology, for example, is, it requires, which we're going towards because we're getting electric cars. But the cadmium, polonium, all sorts of heavy rare earth elements are found in abundance in space. So it's getting that. You may think, one can think of it as unfortunate, but it's getting that. It's becoming economically viable. There's not really any scientific reason for sending humans back into space, men or women back into space. But it's expensive to do so. So parallel to that kind of interest is the development in small technology, in robotic technology, and it's much easier and cheaper to send robots into space, to send rockets which don't require us to sustain human life. Even on trips to Mars, for example, we run an undergraduate project in the first year of the undergraduate degree course, when the first years arrive, mission to Mars, and we get them, split them up into groups. It's largely so they can meet their peer groups and so on, and they have to design. They get help from lecturers, but they have to design a sustainable mission to Mars to get astronauts there and back again. So they've got to think about oxygen supply, food supply, fuel supply, how they're going to protect against radiation, and how they're going to get back, or are they going to come back? They have to think about a lot of different things. But that's too complicated for the future, really. In reality, it's too expensive. But we've sent probes out to the edge of the solar system, right? So that's probably the way to do it if we're going to explore space in any way.
It's quite sad to think, though, that we've gone from the kind of exploring, exciting, why are we here and stuff, to the more kind of like almost raping and pillaging of the universe just for our own. Do you know what I mean?
It's not good, is it? It doesn't have a good feel, does it? No.
It's like we've not even left Earth, and it's like there's fucking loads of metal out there. We need to get it back.
I'm afraid I agree with you. Yeah, I do agree.
It takes away from that young kid who looked up at the stars and thought, "Wow, let's try and understand this."
Let's try and see what we can get.
Yeah, let's get all the battery bloody things we need.
Yeah. But how long would it take? Is it about a year to Mars and then a year back? Is it, or is it?
It's about that. It'd be the order of that, won't it? Obviously it depends how fast you go, but I think propulsion mechanisms could get you there and back in maybe a bit longer, a couple of years or something like that.
Oh, imagine
but
that.
It would almost certainly be one way. It would almost, you'd have to get volunteers who would agree to go to say Mars to try and set up a little colony or something, and if they didn't, then there would be no chance of them coming back.
God, imagine that.
So one-way ticket, I'm afraid.
Throwing your name into that.
Absolutely, yeah.
Would you want to do it?
No, not a chance. One way.
No, would you?
Never. I never got into astronomy thinking I'd become an astronaut. I went on the London Eye, not so long ago, 20 years ago or something, and I was on the floor of when it got to the top of the wheel, because it was just so. No, I'm not very good.
No, isn't it funny?
Not.
Isn't it funny though, Chris? Your whole life is taken up by what's outside the Earth, and yet. I don't mean to put a damper on it, and yet you'll never go there, or you at least. Yeah. Do you know what I mean?
Yeah, I do know what you mean. My son, because he's doing biology, he's at university now, And I talked to him about doing astrobiology, because we talked a little bit about life in space and so on, and that's a really burgeoning area. And he said he didn't want to do astronomy. He said he was scared by the big numbers and the awesomeness of space, and how little it made him feel, and how little the Earth was in this great cosmos. He said that was unsettling to him, and so he didn't want to do it, which is an interesting point of view. I never thought.
Well, I've never
have that effect.
Yeah, it's really interesting. I mean, when you've mentioned about the astronauts come back, I've never thought of it like what you do with your life when you get back.
Yeah.
What
do you do? You've been to the moon. What do you do?
Yeah, there's no bigger.
There's only two others you can talk to. Well, there's more. So there's more since gone there, but you can. When you're at home, when you're on your own overnight and you're trying to get to sleep, you're going to think of that, aren't you? And it really is a self-defining moment. I think to have that as your recent history, that you've gone to the moon.
And imagine Richard Branson recently, didn't he? He went up just into like space and then came back down within like 4 minutes, and obviously it must be incredible, but standing on another planet and looking back, and obviously there's that famous photo, isn't there, where I think it's the most viewed photo in the history of like human race or whatever, and looking back on that
Earth rising
just above the moon, and like, I mean, I can't imagine the like balls of steel first off, and then just looking back and thinking that's so perfect there, just sat beneath that like dark background,
Yeah, it is. It's incredible.
Incredible.
Do you find yourself creating like a day-to-day basis, though, when you're kind of coming through? You must have moments throughout your career where you just think like, this is just incredible. Do you know what I mean?
Yeah, you do. I mean, that sort of side of it, I think, on a day-to-day level, doesn't really, it wears off, obviously, because you're busy with other things. But the idea that you can, I mean, one of the great things about astronomy research, or astrophysics research, is that it's ideas-driven. So, I mean, not so much now, but earlier in my career, you could come up with an idea, it was on the bus or in the bath or wherever, and then pursue it the next day as part of your research. And you could write a telescope proposal to use one of the big national facilities that the UK owns, and Europe or in the US. Use those, get some data, write a proposal, scientific proposal. It gets peer reviewed. If it gets time, then you'll get a chance to collect the data you want to collect, bring it back to your lab or your office, and analyse it on a computer, and make discoveries and write papers about it. And that cycle is a fantastic way of spending your career, because you find it's self-driven research through the nature of ideas, and ideas change, so the nature of the experiments change.
Yeah, I love that.
It's a great thing to be doing.
I love that idea about ideas, and just as humans, how amazing we are, in the sense that I think it was when Henry Ford, created the cars. If he said that if anyone had asked him, how can I improve things, he would have said faster horses. No one said a car, because
That's right.
It was his idea.
That's right. That's right. That's a good point. Yeah, it's a good way of saying it.
Yeah.
It's just not more of the same. I mean, that's how science progresses. It goes a certain way, faster than horses or something like that. You have an idea or theory that develops and gets a bit more complicated, and then suddenly there's a big change, and someone suddenly realises, look, if we do it this way, different way, it all simplifies and all makes sense.
Yeah.
And, you don't have to work so hard. That's happened many times in science.
For you personally, where you are, or where not so much where you are personally working on things, but is in your whole work, what do you think of the kind of big exciting things we've got to come in the near future?
Yeah, no, that's a good point.
Chris, just come a little bit.
Oh, sorry.
Yes,
of course. No, that's fine. I think the thing I'm working on now is a survey called the area I'm working on is low surface, what we call low surface brightness science. That may seem a bit boring, but if you look out into space, most of the objects that you see in images, Hubble Space Telescope images and so on, I encourage people to do that. Just go online and Google HST, Hubble Space Telescope. But most of those objects are high surface brightness. In other words, most of the light coming to us from them is concentrated. It's emitted in concentrated forms, whereas a lot of the light actually in the universe is much more spread out, and it's actually quite a significant amount that's actually spread out. In fact, most of the galaxies are in what we call a diffuse nature, but we don't understand a lot about those populations because they're very difficult to detect. So there's a number of telescopes that are trying to probe this, what we call low surface brightness regime, and one of them is what's called the Vera Rubin Observatory, which is an American project. It's been built in Chile, and it's a large telescope. It has a very large primary mirror with a 6-degree field, so larger than the size of the moon, significantly larger than the size of the moon. And it's going to take very deep images over a long period of time, and that will enable us to probe some of the very, very distant galaxies that we so far haven't been able to pick up.
Right.
So that's one area. I think the UK is involved in it. We've brought in UKRI, the Science and Technology Facilities Council, funding that and part of a bigger project to do that. But it's a worldwide project, and most astronomy projects now are worldwide. You don't sit in your office and go out overnight and look at the stars. It's through a telescope. You have to collaborate. Do you
have to I know. So again, it might sound like a stupid question, but like the Hubble telescope and things like that. Can you just, because obviously you're in the field, can you like apply for them to look at something for you? Like you can literally like as if book it.
Yeah, you can. I mean, it used to be when I was younger, you used to have to go to the telescope. So you applied for time in the same way. There were generally national facilities, UK owned telescopes in Australia, Hawaii, La Palma, in particular, in optical telescopes. And you used to apply, and there will be a telescope allocation committee that would look at all the applications. There'd be a deadline, probably 2 a year, and they give the best ones telescope time, and then you'll fly out to those telescopes, do the observing, come back, look at the data, and analyse the data. More recently, the technology has been such that you can do this over the internet. So it's quite a number of years since I've been observing, for example. And PhD students more and more coming into the field don't go observing as much.
Don't fly out to these different.
Don't fly out to these telescopes, not nearly as much, because they can get the data online.
But that must be so. I can imagine, Chris. Like that would be half the appeal is flying to Hawaii in the middle of the night. It's I don't know. Again, I'm sort of oversimplifying it here, but like they're enormous, aren't they? Like you move it into place, and then you're in this on the top of a mountain in the middle of the night. Yeah. Like that's so cool, isn't it?
That's the romantic bit about it.
Exactly. Yeah. Use that word. It is. It's a romance about it that's to some extent been taken away.
Whereas if you're just getting raw data back, then it's like...
Yeah, I agree. I do agree with that. And it also removes you slightly from the idea that what you're engaging is a scientific experiment. It's actually a scientific experiment. So, you've got to be careful, particularly again for young researchers, that we try and encourage that they understand how the instrument works enough to be able to really understand their data and understand what the limitations of their data, the uncertainties and so on. And that's more difficult, I think, if you're dealing with survey work, survey instruments. On the other hand, the key thing about survey work, the advantage, is that you have lots and lots, millions of galaxies already have information that you can use to do science. And it's not just observations, there's also simulations. So we have a big team in Liverpool who are looking at the properties of galaxies just from simulations they run on big computers, big simulations which involve gravity and radiation, starting off from the properties of that in the very early universe, running it through cosmic time, and then looking at how the properties of galaxies, for example, change with cosmic epoch. And they make predictions. They say, well, if you guys could observe, galaxies at this redshift, you'll see that effect. And in that way, we can change the theory, change the observations. Remember what I said about dark matter and dark energy, and we can change the fractions of dark matter and dark energy to fit those observations, because that's in the nature of predictions and verification that makes science work. So the surveys do have an important role, there's no question about that. It's just a shame that a lot of students don't get the chance to actually partake in an actual observing trip.
And I imagine when the Hubble telescope got launched, and then some of the photos that came back, and it's just, the photos are insane, aren't they?
They're amazing, aren't they?
They're incredible. Incredible.
The detail.
The detail, just... do they alter those images at all? When you see that, they've got incredible colours.
Instagram filters on there.
Because some of do they alter it at all?
They do. Well, they reduce it. If you look at the raw images, they'll have all sorts of systematics on them. So they have to reduce it. In other words, they have to clean it effectively.
Shall I just type in here Hubble telescope images?
Yeah.
How beautiful are some of those?
They're colour pictures that are tuned reasonably accurately to the. You've got 3 filters in your eye to measure colour. The colour's quite subjective, of course, but they're real representations of how you would see it if you had eyes that powerful. But of course you don't, so you don't see it.
So they do kind of alter it as if...
Yes. So the blue there will be the hotter gas, for example. The red will be the cooler gas. The stellar light looks there as a yellowish, but that's what we see in the sun. Right. So that's correct. So it's using filters a bit like our own eyes to come up with that colour pattern
to describe the image. Really,
But those filters are not exactly the same as the ones we have in our eyes. But they're good representations.
See, like this. That's just insane. What is that, Chris?
I think that's a stellar laboratory where stars are being formed. That's in there cocoons of stars, very young stars, what we call protostars, buried in gas, and they will eventually shine through. Some of those you could actually not quite see there, but you can actually see the stars embedded in those big gas clouds. But it looks something like from a Victorian novel, doesn't it? It looks like a great big eagle or something with a snake behind, just trying to.
It's amazing how though, as humans, though we've again with technology, and we've got this information now. It's incredible how clever how clever people like you are to
Gothic novel. It is. They're staggering images from HST.
You know what? This is going to start off or sound a bit like a piss take, and no disrespect, just see the funny side to it in a minute. But do you ever watch Mock the Week?
I have seen Mock the Week. Yeah, I've seen it.
And Frankie Boyle was on there, and he took the piss a bit. It was a funny joke, and you'll see where I'm coming to with it. I think scientists come out that week and was like, they'd found that if you got some boiling water, you put a frog into it, it'd know it was hot and it'd jump out. But if you put a frog in the water, then heated the water up, the frog couldn't tell the water was getting hotter and would die. Apparently that was it. So as him obviously being the comedian took the piss, he's like, you'd think scientists are going to be trying to cure cancer, but no way they are, saying, hey John, how many polos can we feed this parrot before it chokes? And he made the joke about why are they doing this on a frog, and I guess to relate it to you, like people would say, why are we trying to find this out? How is this gonna help? For example, some of the area you're speaking on, it is fascinating. It's blown my mind, but the guy in the street to be like, why do we need to know that? Do you know what I mean? Like the question trying to.
Well, I think there's broadly two types of answer, 3 probably, but let's say 2 types of answer. The first is because, as we said before, it's exploratory, and it's intrinsic. These are intrinsically interesting questions about nature and about our world. And we don't know what they're going to discover. We don't know what we're going to find, and we don't know how that's going to impact our knowledge and eventually our technology. I think the other side of it is that it's motivational for young people, and I think that's absolutely key.
Yeah, massively. Yeah.
It particularly going all the way back to primary school, infant school, all the way through, and it helps to captivate their imagination and to bring them not just into astronomy, although that's good, but into maths, into physics, into biology, into IT, and that eventually it helps the economy through research and development, and some of the the inspirational stuff that you guys are doing, for example, which is also the internet. It's all developed from scientific endeavours that had nothing, and at least initially, to do with those particular subjects. I mean, you probably know more than me. I'm not an expert, but the internet was developed at CERN, where they're looking at by particle physicists who wanted to exchange information.
Yeah, that's incredible. That.
Yeah, so I mean,
they didn't start trying to do an Instagram thing, did they?
No,
you know what I mean. No, it's so true though, isn't it? Like that started, and look what the internet's provided us now.
And some of the things from space exploration that they've found, and some of the technologies that we use, like in cars or like GPS, or it's all come from.
Exactly. I mean, the classic one, of course, is non-stick frying pans. Right? From the Apollo. But yes, you're right. It's much more general than that.
Yeah.
A lot of the technology that we now take for granted was first developed for specific applications. And
just that interest as well. Like I've I said to you on the phone, Chris, I'm lucky in the sense that my dad had got a telescope, gave it to me, and the amount of times I don't look at anything other than the moon, because it is the most incredible thing, and it follows as the Earth rotates. Is pretty clever. A telescope just tracks the moon, and the craters and the detail that you can see on it is insane.
Yeah,
it's just mind blowing.
Yeah. And I think the other thing to say is that it's relatively quite cheap. I mean, we do spend significant amounts of money on it, and as I say, it is a privilege to be able to use public funds to do this kind of research. But it's done very carefully, and it's done with resources that are a small fraction of what, for example, the government spend on other things. Small fraction. So you get a lot of bang for your buck with this kind of work, I think.
Yeah. Oh no, I wasn't suggesting, by the way, anyone would think, well, what?
No, it's a good question.
No,
you have to ask that question because there is significant amounts of money spent, and these new facilities are not cheap. There's no question about that. And the scientists, astronomers, with the help of the UK research councils, have to prioritise the experiments that are done. There's no question about that. But that works quite well. We have, the UK has good links with Europe through the European Space Agency and it's called the European Southern Observatory. So the European Space Agency essentially deals with the satellites, and we're involved in some of those in national agreements. The European Southern Observatory is the ground-based telescopes, essentially in Chile, basically. I've been to many times. And Britain is part of those, and we benefit greatly from those because we can lead international projects and collaborate internationally as a result of that. Yeah,
they had that big kick-off recently, didn't they, in Hawaii, with the telescope that went on top, because it was on like sacred land, wasn't it?
Oh, did they?
Yeah. And I think this is an important area. I think if you think about if you think about representation of minority groups, for example, it's quite important that this kind of technology is seen to be sensitive to people's rights and to people's history locally at these sites. I mean, astronomy facilities, the observatories, are usually built well away from big cities on high mountains, and they're often remote, serene places, and they do have significance for the local people. It's particularly true in Hawaii, so it's important to be sensitive to that. I think.
it was the Maori tribe or something like
was
that.
it?
I think it was sacred to them, something their gods or something.
Yeah, the local Hawaiians is sacred.
I don't know if there's anything else you want to touch on, Chris.
I feel you could have done a podcast on like a tiny little thing.
Oh, on 8
just
subjects we've talked about.
We ended round quite a bit.
Which
I didn't anticipate the questions you were going to ask. It wasn't scripted, was it?
No.
But I could have, I was going to talk about some things which I hadn't talked about, but then we did talk about other things, so that's fine.
But, I mean, Chris, I'd love to do a part 2 maybe in a few months if you.
That's absolutely fine.
If I mean, not that I haven't enjoyed this, I've absolutely thoroughly enjoyed this.
And I apologise for any stupid questions.
There are no stupid questions.
The mind-boggling thing that I will take from this is the twin example you gave.
The twin paradox. It's called. It's not really a paradox, but they call it the twin paradox. Yeah.
How?
Yeah, go and look it up. It's all on the internet. Go and look it up, and you'll see the explanations. But it's a real effect. It's a real effect.
I think that for me, the idea, the analogy about if you put stick coins to a balloon and blow it up, and it just you can imagine something so big, and you just constantly
going round. Yeah, and you know what? From an outsider looking into your world, it seems like you can try and be as clever as you want, but those analogies are so perfect because it just the easiest thing in life. Sorry, the hardest thing to do in life is to keep things simple, and when you give analogies like that, it just simplifies everything. You don't need to be incredibly complex. That it just simplifies it really nicely.
Well, I hope it wasn't too complex. And these are complex ideas, but it's part and parcel of my role and other astronomers' role to try and put them in a way that's accessible, to people like yourselves and the audience. So I hope that's.
I think you make it a great point at the end of one massive part of this is to inspire and motivate. Yeah, I mean, when I was a kid, I still remember now the project I done in school. Googling all the planets, and one of the best projects I ever did, one of the best marks I ever got as a kid and stuff. I absolutely loved it, and just the idea. So hopefully it can give people a little toe in the water about
it. Of course, recently we did a great injustice to all that history of schoolwork that the teachers have done by removing Pluto as the 9th planet. Well, always 9th planet, and the last one was Pluto. It has now been relegated down to one of the minor planets, I think.
Well, my 6-year-old has been learning about it, and we're going in order of the planets and stuff, and I still remember, so pathetic this is. Well,
many vile earthlings, that one.
Well, we had, as a class, we made up our own one. Do you remember the supermarket, Netto?
Yeah.
I remember Netto.
So we had my very energetic mother jives secretly under Netto posters. That was like the one as a class. The teacher got us to make our own one up, and so I still remember it as that. And my 6-year-old comes home and she says the planet's in order, and I misses out Pluto, and I said, "You've missed out Pluto." She said, "No, it's not a planet."
She said, "No, it's not a planet."
I said, "Yeah, it is." I said, and I'm arguing with a 6-year-old, and she's like, "Dad, it's not a planet."
No, they will teach that now. Yeah.
So what was that then? Just because of more work was done?
I think because it was too small. Basically, I think that was the idea. When you look at its orbit, you realise it's not really a planet as they think planets formed. You think its neighbours are these big gas-rich giants like Uranus and Neptune, right? So you've got, you think the planets basically get bigger as you go out. You've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then you've got tiny little Pluto.
Another one, just like, I know we're going to wrap up now, but on that one as well, you know what other mad fact I think it's a fact, I mean, tell me if I'm wrong, that all the planets could fit inside Jupiter?
That's true, I think.
I'm sure that's... Yeah, I know, because I always think, how is that...
That may be right, though. I think it's because Saturn would take up... I'm not sure about that. I'd have to think...
if you squashed them all down and you fit them all in...
that may be true. That may be true. Jupiter is by far and away the second biggest object in the universe. In the solar system.
In the solar system,
the solar system. And it gives off more heat than it actually absorbs. It's like almost a very cool sun, you can think of it as. It's not burning. It's not burning nuclear fuel, but it's slowly contracting because of its size.
And is that the one that's got the sort of hurricane, the spot?
red
Yeah,
spot.
the
Yeah, red spot.
400 mile-an-hour winds that have been going on for hundreds of years. Yeah, that's right.
It's like that thing on YouTube, if you ever see it, and it's like a time scale, pretty much of what we spoke about, and it says like, you know, you're here, it's a dot. I think it starts off at like a Google image of like someone having a picnic, and then it goes out, then you see the Earth, and then you see the moon.
That's right.
It just
Have
keeps
you seen
on.
that? That's really good.
It keeps on going out,
Yeah,
and then until our own sun is tiny,
yeah,
and then it's like the next sun, and then the next sun, and like another unit, like,
yeah,
and you just, that's when I just go ahead.
yeah. And have you seen the one that goes in as well? So it's one that starts with a picnic.
Yeah, I've
and
not
then
seen it the other way
Yeah,
around.
and then it zooms into the grass, and then a blade of grass,
That's cool.
and then the like the fibrous structure of the grass,
Yeah,
and then into a molecule, and then into a stream of molecules, into the DNA, into the DNA of the grass, into an atom, and into molecules, and an individual atom. An individual atom, you see the electron going around, and
looks a little bit
most
then
of it's
like,
empty space. It looks
Yeah.
like a little solar system, and then right into the nucleus, into the nucleons, the protons, and the neutrons, into the quarks. And I think there's one where you go.
try and get it up, Tom, if you can.
What do I type in here?
Like distance of solar system or something.
Yeah, it's called. It is distance.
It's a solar system or something, or measured in solar system or
it's,
something.
distance scales.
Distance of scales.
Distance scales or something.
Unit of the solar. Let's
So it'll
search
come
it.
up if you type something like that in now. It'll
No, that's map reading.
yeah, put in universe in the title.
Atom. Put atom. Yeah, atom to universe.
Yeah, I think it might be the first one. You know,
You're unbelievable.
it's. I think I saw it on Twitter. Something that said,
Oh right,
you know,
so it was a lot because that's
it
10
was like-
minutes long.
if you're having a bad day, something like that. This is you
I can't remember.
in the solar system or something.
Atoms.
Atoms to. It's called the scale of the universe. Atoms to the cosmos or something. Atoms to galaxies.
It makes you feel incredibly small and worthless anyway.
Oh, I need to find this.
Oh, that's it.
Is
Yeah,
that
that's it. Yeah, Cosmic Eye.
Cosmic Eye for anyone who's listening.
Yeah, it's 3 minute long. It's called the Cosmic Eye.
Right.
And this will make you realise just how.
Oh, so this is the one that's zooming out then.
10. Yeah.
Watch
There's one
this.
called powers of 10 as well.
So she starts off lying in a field,
God.
and it's just like Google Maps, essentially. Well, it is, yeah, Google Maps. In fact, Google must have done this then from their headquarters.
Yeah. So it's started in California.
Starting in
then.
California, it just comes out.
Even the scale of the US. US is huge, isn't it?
So you think, right, there's Earth, and then Earth looks tiny.
There's the moon.
Yeah, and it's what's that say at the bottom? So 10 million
10
what?
million, 100 million. Going up in
Kilo.
factors of 10.
All right, kilometers.
So that's our solar system
That's
there.
the.
Yeah.
That's the.
Cupid. What's that? Cupid.
So that-
The solar system just disappeared.
Can I just pause that a second just to how, you know, when we were talking about Voyager 1 and that it's got this gold disc on and it's going to, I mean, it has hardly got anywhere. There it is there.
Yeah, it's got
Yeah.
out of the solar. It's just got out of the. It's called the troposphere, isn't it?
Really?
The magnetized, the ionized radiation from the sun. At some point, it goes neutral because it's blasted off. It's all ionized, it's hot gas basically. But at some point, it neutralizes. And I think it's just got out of that.
Just got out of that.
So it's formally out of the solar system. Yeah, but you're right.
So in space
Very
terms, it's
far.
hardly got anywhere. It's just got
No.
it's got next door really.
That's right. This is now the Milky Way that you're seeing.
1 light year. 10 light years.
Neighbouring
This is the local
stars.
neighbourhood, the local stars. The stars close to us. Some of the constellations are whizzing by there. Now you're seeing the larger scale of the galaxy. You see where we are on the galaxy. We're not in the centre of it. We're on the edge, on the spiral arm. Now you see the local group of galaxies. The Milky Way is Andromeda close to us, and this is a large-scale structure. This is from simulations that I was mentioning.
So that's 1 billion light years.
Yeah, So you see there the structure, all that material is the dark matter, and you see it all clustering. So you see the high density regions of matter, and also the low density regions where there's not much, which are called voids. I've done some research on those as well. But that's not it yet. As you go out even further. Oh no, we're coming back in. So you haven't got the cosmic background radiation there. That's fine.
So where were we there? That was 10 billion light years, I think it was. It got up to
10 billion light years. That's it.
10 billion.
Yeah, it's just
light years.
It's just madness, isn't it?
So the universe is about, as you said at the beginning, 13.7 billion years old. So 10 billion light years is about just less than the age of the universe. Between there and the edge of the universe, if you like, I'm going to call it that because there isn't an edge, is the cosmic background radiation, which was discovered in 1965 by Penzias and Wilson. Is the strongest evidence we have for the Big Bang. It's an all-pervading radiation that is actually measured. Its strongest signal is in millimeter wave band.
Right.
So you can.
Something's happened there, and we've noticed a millimeter wave.
Yeah, it's like a millimeter. Yeah, it's like a waveguide experiment that you do at school, or you've got a microwave, so it's similar kind of radiation to that. Not quite as intense as that.
But we've picked that up from that far.
Yeah,
it's
exactly.
come.
Yeah, we have. Yeah,
it's fucking mad, isn't it?
It is crazy.
Isn't it crazy?
Chris, you know when my dad might have been talking complete nonsense here, but remember when we had before digital TV, but you actually have an aerial on your house, and then when you go on to channel 0 and you see that static, that is in essence from the Big Bang.
Some of it is.
What you see on your TV is in essence
that
part.
old salt and pepper pattern. Yeah, about 1 in 100 of those little flashes are from the other side of the universe. Yeah, signal from the other side of the universe. Yeah, it's very intense radiation. It was easy once it was predicted, and then there had to be a little bit of development of radiometers. There was a group in Princeton, quick story, who predicted it and were looking for it. They were building the radiometers to detect it, and another group in New Jersey were using a telescope to look at the galaxy, and they found this radiation that seemed to be everywhere. They didn't know what it was, and they thought it was something wrong with the antenna that they were using, and they thought there were pigeons nesting in it, and they thought the pigeon droppings were actually causing an electrical dielectric signal. So they cleaned the pigeons out. They did it humanely. But they had actually literally stumbled across probably the biggest discovery in physics, which is the cosmic background radiation, but didn't know what it was. And they published a paper not knowing what it was, and they won the Nobel Prize. And the people who've done all the hard work, I say all the hard work, but
people who are actually
already
looking for it.
Princeton have been recognised recently, actually, one of them at least.
Right.
But at the time, it was quite controversial, as sometimes Nobel Prizes are, even in the physical sciences.
Goodness me.
Yeah, but that's it. Wow. So we can zoom in again.
The
best bit is coming back again. There we go.
Yeah, the when I seen it was like, if you're having a bad day or something, you are literally nothing.
Yes,
on this earth.
Yeah, your problems are nothing.
Yeah. Yeah, it's just. Oh, this is the one where you're saying it goes back into what makes up a person or someone's eye. I think this might be then. Yeah.
Yeah, it is. Yeah, that's.
Here we go. It goes into the eye. Yeah. Yeah.
White blood cells.
Yes, fat people. I mean, I'm just grateful, mate, there are people as clever as you who can just try and, guide me through things, because it's just mad, isn't it?
Then the DNA.
It ends up looking like space again.
It does. It does after a while.
1 picometer. 100 femtometers.
10 to the minus 15 of a metre, I think. Femtometer.
Up quite, down quite.
That's right into the atom. See, it's all that's empty space in the middle there where you've got. It's going to go right out now, is it? All the way.
Incredible.
Yeah.
So hopefully this has fried your brain as it has mine. No, Chris, honestly, massive thanks again. It's
Thank
been,
you. I've enjoyed it.
Yeah, really, really enjoyed it, Chris. Honestly, I can't thank you enough for your time. Is there anything you want to just mention at all? Anything about Liverpool John Moores, or I know we spoke about it at the start, but anything you want to just...
No? All I would say is look at our website. Look at the Astrophysics Research Institute website if you're interested in astronomy, or the university website. We've got a lot of courses that people can do, undergraduate courses, but also distance learning courses, as I mentioned, at different levels, master's courses, which try and bring these ideas to students, both in terms of teaching them some of the fundamentals of the subject, but also these exciting results, new results that we've been talking about.
Brilliant.
And as I say, the institute is blessed with people who know a lot about these subjects and teach on courses in which they're also research experts.
Yeah. Fantastic. I'll put the links below as well, mate. So.
Yep. Brilliant. Thank you very much.
Cheers, Chris.
Gentlemen.
Thanks, mate.
Thank you, mate.